Hello everyone and welcome back to the You Can Do TV channel. In today's video, we will learn about the open die forging process and the production of essential mechanical tools such as wrenches, screwdrivers, and pliers.
The Anyang 18T open die forging hammer represents a remarkable advancement in forging technology. This machine is specifically engineered for the purpose of forging valve bodies used in petroleum pipelines. Its robust design features a ram weight of 20,500 kilograms, capable of delivering a maximum hitting energy of 630 kilojoules. To enhance the forging process, an absorber is strategically installed under the anvil, ensuring that operators do not experience significant shaking during the forging operation. One of the most remarkable features of this hydraulic forging hammer is its utilization of a fully hydraulic drive system. It falls under the C66Y series, which offers a variety of structural types including single arm, arch, and bridge configurations. The fundamental principle underlying its operation is maintaining a consistent high-pressure oil supply in the lower chamber of the hammer rod piston. This setup allows for precise control of the upper and lower oil pressure, resulting in controlled and efficient striking. The technical characteristics of this hydraulic forging hammer are equally impressive. The fully hydraulic power drive system eliminates the exchange of oil and gas, significantly extending the lifespan of the hammer rod piston seal. During the return stroke, the upper cavity experiences low back pressure, preventing any boring interruptions during striking and improving both return speed and striking frequency. Furthermore, the unique X-shaped guide rail structure is a notable innovation that doubles the lifespan of the hammer rod, transforming it from a wearable part to a longevity part. The striking valve is designed on the principle of differential servo, offering an extremely flexible operating system that facilitates precise control of the force of the strikes, whether they need to be light or heavy.
Open die forging, also known as free forging, is a drop forging process where metal is deformed into desired shapes without any limitations between the top and bottom anvils. Unlike closed die forging, open die forging allows for flexibility in shaping and operates with relatively simple production equipment, resulting in lower costs. This forging method is particularly suitable for heavy machinery equipment and plays a vital role in producing important parts. One of the key advantages of open die forging is the elimination of defects found in casting blanks, such as shrinkage, gas holes, and porosity. As a result, products manufactured through open die forging exhibit higher mechanical properties. However, it's important to note that the shape and dimensions of open die forgings are primarily controlled by manual operation. Consequently, the size accuracy of the products is relatively lower, requiring larger machining allowances and higher working strength. Therefore, open die forging is mainly employed for single and low volume production. Open die forging equipment consists mainly of forging hammers and hydraulic presses. The commonly used forging hammers include air hammers and steam hammers, while hydraulic presses utilize static pressure produced by liquid to deform the blanks. Hydraulic presses are particularly necessary for producing large forgings. The basic open die forging process encompasses various operations, including setting, drawing out, punching, bending, torsion, mismatch, cutting, and welding. Drawing out, also known as elongation, involves reducing the cross-sectional area of the blank while increasing its length. This process is commonly used for forging rod and shaft parts and can be carried out on a flat anvil or by drawing out on a core shaft. The latter involves inserting a core shaft into a punched blank and gradually drawing it out to achieve the desired length while maintaining the same inner diameter. This method is suitable for sleeve-type forgings. Ipsetting is a forging process that reduces the height and increases the cross-sectional area of the blanks. It is often employed to produce gear blanks, ring blanks, and more. There are 3 types of ipsetting: completely upsetting, end upsetting, and middle upsetting. Each type is used based on the specific characteristics of the forgings and the desired outcome. Punching involves creating holes in the billet by either rushing through the material or creating unthreaded holes. Bending is performed to shape the forging using specialized tools or molds. Cutting divides the billet into sections or removes a small area from one end. Mismatching refers to moving part of the billet a certain distance while keeping the axes parallel. This technique is commonly used in forging crankshaft parts. Like any manufacturing process, open die forging can experience defects. Some common defects include cracks, which can occur due to poor billet quality, insufficient heating, low forging temperature, improper cooling methods, or inappropriate forging techniques. Other defects include depressed deformations on ends and cracks along the axis. These issues need to be addressed to ensure the quality and reliability of the forgings.
This is one of the world's most powerful bucket wheel excavators, BG290. It is mining brown coal at an open-pit coal mine in Germany. The hydraulic steering mechanism ensures it navigates precisely through the grounds. Its enormous hydraulic cylinder weighs 30 tons with a piston diameter of 1,000 millimeters and an overall stroke of 4,400 millimeters. After a long period of operation in harsh conditions, the cylinder degraded. It had to be dismounted and then really reconditioned. Master craftsmen from Montanhydraulik GmbH, Germany, have been selected to carry out this difficult project. There are 7 requirements had to be fulfilled urgently within 21 days to minimize excavator downtime. Renewal of the sealing elements and guideways. Chrome, nickel coating of the piston rod. Design and manufacture of a protective cover against falling stones. Inspection and reconditioning of the valves mounted on the cylinder. Replacement of the hinge bearing. Honing of the cylinder tube. Renewal of the anti-corrosion coating and sandblasting. A new protective coating is applied to the tube before welding is performed. Pressure testing and refilling with hydraulic oil. The piston is manufactured completely using CNC machine and others. The threads on the rod and piston are lined up again. It is a tense moment. Another protective coating successfully installed to the cylinder. The mounted piston rod package is pushed into the cylinder tube. They are connected by giant bolts and nuts. The installation of valves and tubing is undertaken finally. The protective cover is mounted and adjusted. (2,500 liters of hydraulic oil is filled into the cylinder and tested. At this point, all work is done and the hydraulic cylinder is ready to return to the site for installation on the excavator. Upon arrival, the installation of the hydraulic cylinder into the bucket wheel excavator was carried out immediately. Then the BG290 is ready to resume its regular work.
The production process of steel rods begins by heating the billets in a reheating furnace. High-pressure water jets are sprayed on the heated billets to clean off any oxidized parts. AKS, a steel manufacturing plant in Bangladesh, has state-of-the-art descaling devices that prevent spot cooling during the descaling process, as maintaining a constant temperature is crucial for producing quality steel bars. After descaling, the billets are sent to the rolling mill. AKS uses a rolling technology that combines horizontal and vertical stands. This unique feature allows them to roll the billets into desired shapes without continuous turning, which can harm the inner particles of the billet and reduce the strength of the steel bars. The combination of horizontal and vertical stands avoids this issue and increases the density of the material. The rolling mill at AKS consists of a roughing mill with a production line of 18 mills, ensuring the production of high-quality rods in the shortest possible time. The rolling process is followed by the thermomechanical treatment, TMT, of the steel bars. This involves passing the heated bars through a high-speed cooling system, which creates temperature differences between the core and surface, resulting in layered steel bars known as DMT steel bars. The cooled steel bars are then transferred to a cooling bed, where they further solidify. AKS has the longest cooling bed in Bangladesh, measuring 120 meters. Once cooled, automated machines are used to bind the finished steel bars together for easy handling and transportation. Manufacturing process of wrenches. Yanni's Way, known for its complete range of high-quality wrenches, follows a meticulous manufacturing process to ensure the durability and performance of their products. Raw material. Jones Way wrenches are made from premium steel. The raw material is heated to 1000 degrees Celsius to increase its overall strength and reduce potential stress concentrations. It is then elongated using a rolling machine. Forging. The rolled steel is sent to the forging press. The forging process involves 3 die pressings. The first die presses out the general shape of the wrench. The second die presses the finished shape. And the third die cuts out the blank. Chemical grinding. After forging, the wrench blank undergoes preliminary chemical grinding. It is placed in a container with a chemical solution and ceramic stones that grind off the ragged edges, ensuring a smooth surface. Polishing. For Jonesway W26 mirror polished wrenches, the wrench blanks also undergo hand polishing to achieve a highly reflective surface finish. Stamping. Once the technician ensures the correct size, the wrench is placed on a press for stamping. A specially designed mold is used to stamp the Jonesway logo, size, and item number onto the wrench. The stamping process also fortifies the hardness and metal structure of the wrench. Heat treating. After stamping, the wrench goes through the heat treating process to maximize the strength and hardness of the metal. This step enhances the overall durability of the wrench. Sandblasting. Following heat treating, the wrench undergoes sandblasting to clean up the carbonized surface. This process removes any remaining impurities and enhances the effectiveness of subsequent surface treatments. Chemical grinding for mirror polished wrenches. For Jonesway W26 mirror polished wrenches, an additional round of chemical grinding is performed to achieve a finely polished finish. Open-end grinding. The open end of the wrench goes through 3 grinding stations to ensure precise dimensions and a smooth surface. Cleaning. The technician cleans up any lubricant residue from the wrench and trims off sharp edges that may have resulted from the production process. This step ensures the wrench is free from any contaminants or potential hazards. Plating. The semi-finished product is then subjected to a plating process. Jonesway employs a specially designed plating technique that enables the plating material to be deposited on the tool surface more effectively, resulting in a perfect surface treatment. Testing. The entire batch of finished wrenches undergoes sample inspection conducted by a Jonesway professional quality control engineer. Packing. Once the finished products pass the quality inspection, they are ready to be packed for delivery.
The manufacturing process of stainless steel flanges begins with the careful selection of the appropriate stainless steel grade, in this case, Super Duplex. Super Duplex stainless steel is known for its exceptional corrosion resistance and strength, making it an ideal choice for demanding applications. The selected stainless steel billet is heated to a precise temperature, allowing it to become malleable and ready for forging. The precise temperature control is crucial to ensure proper material flow during forging. The heated billet is placed between the closed die set, which contains the desired flange shape. A massive mechanical or hydraulic press exerts immense pressure on the billet, causing it to take the shape of the die. This process ensures a high degree of accuracy and strength in the final flange. The flanges meet the strict quality and performance standards required for offshore and energy industry applications, ensuring superior corrosion resistance and mechanical properties. After the initial forging, additional blows are applied to refine the shape and further compact the metal, enhancing the structural integrity of the flange. A clipping tool is used to remove excess material from the forged flange. The flange is then subjected to precision machining processes to achieve the exact tolerances and surface finish required. The final product undergoes rigorous quality control measures, including inspection for dimensional accuracy, material integrity, and surface finish. Next, we will visit the factory of Tecnorulli company, based in Italy. Tecnorulli designs and produces rollers and machinery for conveyors with more than 40 years of experience. The production of rollers and drums includes 18 phase. It is divided into a number of automatic and semi-automatic lines subject to continuous technical updating. Accurate quality control is performed on incoming materials and semi-finished products, and after each phase of production, to ensure that the products are manufactured according to customer requirements and in line with the highest quality standards. Automated assembly of rollers with straightness control in output. The phase of assembly of jackets with the shaft and insertion of bearings and seal kits takes place on 5 different subservient lines, also using an anthropomorphic robot and equipped with a system that controls the straightness and correctness of the axial clearance on each roller leaving the machine. Automatic feeding of welding lines. To ensure an interruption-free welding process, a computerized handling system feeds the machines with pre-machined tubes and semi-finished products. Machining of end cuts and bores of tubes performed in line. End cutting units and boring machines pre-machine the tubes with centesimal precision, facilitating the subsequent phases of welding and assembly. Tecnorulli's high-quality rollers and machinery for conveyors have established themselves as an important benchmark for the entire industrial handling sector. In Chisholm, Minnesota, United States, the Triumph Twist Drills Company is manufacturing drill bits. They are a leading twist drill manufacturer, a division of Minnesota Twist Drill. After the raw material is straightened and cut to length the Big Lewis machine, it is sent to the heat treatment room. Bits are dipped in multiple baths containing barium salt for different periods of time to harden the steel. This vibrating roto machine to clean off salt and debris the draw furnace stick on bits. After cleaned in the roto, bits are then put into the draw furnace for tempering, which makes them less brittle. In the next step, bits are sent to ending. Centerless, this operation grinds the mid to the final diameter back tapers and creates the roundness. In the cutting process of flute, the flutes are ground one at a time, grinding away large amounts of steel. Clearing process grinds the clearance to eliminate rubbing on whole sides during the drilling process. Pointing process finishes the point, creates the lip relief chisel angle and centrality. In the split pointing process, drills are created, secondary cutting edges split. Drills won't move or walk when starting a hole. The reducing process reduces the size of the pitch shank in order to fit all drill chuck. Flatting is done to help keep the drill bit from slipping in the drill chuck.
This section is a detailed description of the manufacturing process of a screwdriver. Making screwdriver blade, slotted. The process starts by taking coiled steel and flattening the steel tip to the correct slotted size. The edge is then trimmed off, and the flattened tip is ground to shape. Making screwdriver blade, Phillips. The beveled crosspoint of the Phillips drive code is precisely cut using high-precision knife mold machinery. The technician checks the drive code to ensure the screwdriver tip meets the standard. Making flange groove. The technician creates the flange groove on the opposite end of the tip. The flange groove is designed to lock the screwdriver shaft into the handle. The twin flange groove design ensures a firm embedding of the screwdriver blade into the handle, increasing product endurance. Heat treating. After making the flange groove, the screwdriver blade undergoes a heat treating process to maximize the strength of the metal. Sandblasting. The screwdriver blade is subjected to the sandblasting procedure to clean up the carbonized surface. This process enhances the effect of the surface treatment. Plating. The semi-finished product goes through a plating process. Jones Way utilizes a specially designed plating technique that ensures effective deposition of the plating material on the tool surface, perfecting the surface treatment. Injecting handle. The plated screwdriver blade is placed into an injection mold, and a special material is injected to create the handle. This process firmly embeds the screwdriver blade into the handle. Jones Way's color handle design uses different colors to distinguish different drive codes, making it easier for end users to find the appropriate screwdriver. Testing. The entire batch of finished products undergoes sample inspection by Jones Way's professional quality control engineers. Printing. Once the screwdriver has passed quality inspection, the technician prints the size and drive code icon on the bottom of the handle. This feature allows users to identify the size and drive code without picking up the screwdriver. Packing. After passing quality inspection, the finished products are ready to be packed for delivery. The manufacturing process of pliers begins by heating the raw material to 1000 degrees Celsius. This high temperature makes the steel malleable for shaping. The forging process involves 3 die pressings. The first die press shapes the general outline of the pliers, followed by the second die press, which refines the shape further. Finally, the third die cuts out the blank form of the pliers. After forging, the technician grinds the front side and jaws of the pliers to achieve the desired finish. Lathing. After the forging and grinding steps, the pliers move on to the lathing process. Lathing involves the use of a lathe machine, which rotates the pliers at high speed while a cutting tool removes excess material to achieve the desired dimensions and smoothness. The lathe machine allows for precise shaping and finishing of the pliers, ensuring that they meet the required specifications. Assembling. Following the lathing step, the pliers are ready for assembly. A technician inserts a rivet into the broached hole and then presses it to assemble the pliers securely. This assembly process ensures that all parts are properly aligned and connected. Heat treating. Once assembled, the pliers undergo a heat treating process. Heat treating involves subjecting the pliers to specific temperatures and controlled cooling to maximize their metal strength and hardness. Surface treating. After heat treating, the pliers undergo surface treatment. A technician bathes the pliers in a rust inhibitor solution to protect them from corrosion. This treatment helps prolong the lifespan of the pliers. Subsequently, the pliers are dried, ensuring that they are ready for the next stage of the manufacturing process. Testing. The entire batch of finished pliers undergoes sample inspection by Jonesway professional quality control engineers. Manufacturing process of socket raw material. Every Jonas Way socket is crafted using premium steel sourced from Taiwan China Steel Corporation, the leading steel manufacturer in Taiwan. The high-quality steel material enhances the durability and performance of the final product. Cold forging. The coiled steel is first straightened and then cut into short billets. These billets are then subjected to the cold forging process. Cold forging involves shaping the metal at room temperature using high-pressure dies. The billets are placed in a forging press, where they are subjected to intense pressure. This pressure deforms the metal and molds it into the desired shape of the socket. Lathing. Lathing is a machining process used to shape the socket rim. A lathe machine is employed, which rotates the socket, while a cutting tool removes excess material to create the desired shape. The technician operating the lathe carefully sculpts the socket rim, ensuring precision and accuracy. Knurling. Knurling is a process that adds texture and grip to the surface of the socket. It enhances the ergonomics and usability of the final product. Roller stamping. Roller stamping is employed to add the Jones Way logo and item number to the socket. The socket is placed on the twin roller stamp, and the logo and item number are engraved onto the surface. The twin rollers carry the engraved design, and as they rotate, they transfer the design onto the socket. Heat treating. After the roller stamping, the socket undergoes a heat treating process. This step maximizes the strength and hardness of the metal. Sandblasting. The socket is subjected to a sandblasting procedure to clean the carbonized surface. This process optimizes the effectiveness of the subsequent surface treatment. Grinding. The socket then undergoes a series of grinding processes to achieve a smooth surface texture. This step maximizes the effectiveness of the plating process. Plating. Following the grinding process, the semi-finished socket goes through a plating process. The factory employs a specially designed plating technique that ensures effective deposition of the plating material on the tool's surface, resulting in a perfect surface treatment. Testing. A professional quality engineer conducts sample inspections on the entire batch of finished products.
The 13,000-ton large open-die forging press by HBE Press stands as a monumental achievement in the realm of heavy industry machinery. Installed at Bastille, it proudly claims the title of the second-largest open-die forging press globally at the time of its production. Let's delve deeper into the remarkable features and engineering excellence that define this impressive machine. One of the standout features of this press is the use of a flat guide as the moving cylinder's guideway. This design choice is not just a matter of aesthetics, it plays a pivotal role in the press's performance. This guide is a critical component in allowing the machine to withstand the tremendous eccentric forces generated during forging operations. Furthermore, it makes controlling the guide bush much more straightforward, enhancing the overall accuracy and precision of the forged products. The structural integrity of the press is further reinforced by a pre-stress column. This solid combination, which spans over 2/3 of the crown with the main bed, creates a stable and robust structure. The tie rod and column work in tandem to distribute tensile force and eccentricity respectively, ensuring the press's long-term durability. The innovative use of a spherical design in the return cylinder is another testament to HBE Press's commitment to quality and performance. This design effectively prevents oil leakage and safeguards the piston rod and seals from damage caused by eccentric forces. Notably, it also simplifies and speeds up the disassembly process, making maintenance and repairs significantly more manageable. By reducing direct stress, this design choice substantially extends the durability of the piston rod, reducing long-term maintenance costs. Within the press, the main cylinders are an essential component, and their design and assembly are meticulous. These main cylinders are seated upon self-aligning compressed pistons contained within the ram itself. These pistons feature unique surfaces at both the top and bottom, which play a crucial role in reducing oscillating motion, thereby ensuring the quality and consistency of the forged products. The column guide surfaces are designed with ample clearance to accommodate any thermal expansion that may occur during the press's operation, further enhancing its performance and longevity. We are at the forging facilities in Chelyabinsk, Russia, to explore the forging production process. A fundamental step in this intricate process is the heating of raw materials to the precise temperature required for forging. To achieve this, the facility employs state-of-the-art induction heaters. Induction heating is an exceptionally efficient method that leverages electromagnetic induction to generate heat within the material itself. This process is not only highly effective but also allows for remarkable temperature control. In conjunction with induction heating, it has incorporated an auto billet loader into its operations. This loader automates the task of feeding raw materials, known as billets, into the induction heater, greatly streamlining the production process. By reducing the need for manual labor, the auto billet loader ensures consistency and precision in the heating phase. Furthermore, the facility has integrated an accept-reject system into its heating process. This system plays a crucial role in identifying any billets that may not have been heated correctly or exhibit defects. If a billet fails to meet the stringent quality standards, it is promptly rejected, thus upholding the final product's quality. In the case of hammers and presses, In addition to induction heaters, the facility utilizes gas-fired continuous furnaces. These furnaces provide an alternative method for heating the materials, offering flexibility in the production process. To maintain precise temperature control, the gas furnaces are equipped with an automated temperature control system that includes a cutoff facility. This advanced system ensures that the billets are heated to the exact temperature necessary for forging. The heart of the forging process lies in the various machines and equipment utilized in the forge shop. Here, a wide range of machinery is employed to cater to the diverse needs of their customers. This comprehensive equipment includes press lines, upsetter lines, hydraulic presses, and hammers, each offering varying capacities and capabilities. The forge shop boasts 16 press lines, with capacities ranging from 1,000 tons to 6,300 tons. These press lines excel in closed die forging, a technique in which the material is shaped within dies to achieve the desired form. In addition to press lines, there are 10 upsetter lines with capacities ranging from 630 tons to 3,150 tons. Upsetting is a forging process used to increase the cross-sectional area of the material by compressing it axially, facilitating a diverse array of product shapes. Moreover, the facility houses two 1,000-ton hydraulic presses, each equipped with a phosphating line. Hydraulic presses are versatile machines utilized for a wide range of forging applications. Chelyabinsk also operates 10 hammer lines, with capacities varying from 2 tons to 16 tons. Hammers are instrumental in open die forging, a method that allows the shaping of the material without confining dies, offering flexibility and versatility in production. Alongside the hammer lines, there is a dedicated line for a 5-ton open die hammer, enabling the creation of unique and specialized components. Closed die forging is expertly executed on press lines, hammers, and upsetter lines, with the material placed within closed dies and pressure applied to shape it into the desired form. Open die forging, on the other hand, is predominantly conducted using hammers. This method dispenses with confining dies, providing more flexibility in shaping the material. Flashless forging is an intricate technique employed for crafting gears and shafts, and it can be executed on both presses and upsetter lines. This method involves precise shaping of the material to create intricate and detailed components. Hot extrusion is another essential forging technology utilized at here. The facility employs hot extrusion on presses to create hubs, a process that entails forcing the material through a die to achieve a specific shape. For the production of shafts, it employs hydraulic presses for cold extrusion. Cold extrusion, in this context, involves shaping the material at or near room temperature to achieve the desired form. Jankovits is based in Hungary. They are experts in planning, manufacturing, installing, maintaining and repairing specialized machinery and production lines. Jankovits cylinders are uniquely designed and adhere to rigorous standards in various industries. Based on the experiences obtained in the last more than 2 decades, they designed a basic cylinder that is characterized by long lifespan and environment-friendly technology. The seal systems applied are able to ensure protection against leakage, therefore the environmental pressure is low. The rest of the components, hone tube, hard chromium-plated rod, piston and rod gaskets, fasteners, standard size OTC components, are the products of market-leading manufacturers. Prior to delivery and assembly, cylinders are subjected to cyclic running and pressure tests on a final acceptance examination equipment designed and constructed by Jankovits. The manufacturing process of a steel wheel is a fascinating journey that blends a rich history with modern technology to create a crucial component for various vehicles. Steel wheels have evolved over thousands of years, and their design and production have undergone significant improvements to meet the demands of modern transportation. The process begins in the design department, where engineers and designers use accurate calculations and complex models to create the ideal wheel. These wheels are designed to carry heavy loads, ensuring their strength and durability. Once the design is finalized, the production begins. The steel wheel starts as a flat piece of metal and gradually gains volume. Semi-automatic welding is employed to construct the wheel from solid pieces of metal, ensuring that it won't break or cave in during operation. Quality control is a critical step in the manufacturing process. The wheels are thoroughly inspected to ensure they meet and exceed quality standards. After quality control, the wheels can be painted in various colors or simply sent with a protective coating. The final steel wheels are ready for a wide range of applications. Some wheels go directly to their destination, while others become a part of super powerful semi-trailers or other heavy-duty vehicles. Steel wheels like these are manufactured by the millions, serving cities around the world, adapting to various climates and conditions. The Crucible manufacturing process. Crucibles, those vessels capable of withstanding extreme heat and pressure, play a pivotal role in a multitude of industries, from metallurgy to foundry work. The crucible manufacturing process is a meticulously choreographed symphony of materials, techniques, and precision. This narrative explores the crucible creation journey through the lens of key steps: hand shaping, rib forming, roller forming, isopressing, coking, impregnation, spout installation, glazing, inspection, painting, and shipping. Rib forming. While hand shaping embodies the artistry of crucible creation, rib forming introduces precision in manual shaping. This technique is particularly suited for smaller crucibles. It leverages a manual system that capitalizes on mechanical leverage to apply the necessary pressure for crafting the crucible. The forming device, aptly named a rib, is lowered into the mold, which starts rotating as the process unfolds. A hydraulic ram presses the rib into the clay graphite material at the base of the mold. This exerts pressure of up to 5 metric tons, ensuring an even distribution of force. Rib forming results in crucibles marked by uniformity and precision, attributes that are challenging to attain through a completely manual process. The rotational movement enhances the distribution of material, and the automated approach streamlines the manufacturing process. Roller forming. The process begins by filling the mold with the requisite materials, after which a stainless steel roller is introduced into the spinning mold. This roller applies controlled pressure to the material, effectively displacing it and compressing it onto the mold's bottom and sides. The result is a crucible characterized by exceptional thermal conductivity, impressive thermal shock resistance, robust mechanical strength, and outstanding refractoriness. Additionally, these crucibles boast exceptional resistance to damage caused by fluxes, making them indispensable in high-stress industrial settings. One notable feature of roller forming is its flexibility. Molds and rollers can be interchanged to adapt to various crucible sizes and shapes. Moreover, this automated process guarantees uniformity and consistency across all crucibles produced. Isopressing. Isopressing, or isostatic pressing, stands as a distinctive approach to manufacturing crucibles. This specialized process utilizes a liquid or gas medium to apply uniform and simultaneous pressure from all directions on the material being compacted. Isopressing finds application in crafting a range of crucibles, such as Si-carb clay-bonded graphite crucibles and Ultram melt carbon-bonded silicon carbide crucibles. The fundamental principle of isopressing is the meticulous positioning of the core before the mold is sealed and transferred to the pressing chamber. The air and overhead material dispensing system are employed to fill the mold with clay graphite or silicon carbide material tailored to the specific crucible being crafted. Once the mold reaches the isopress, it is loaded onto a lift that lowers it into the pressing chamber filled with water. The isopressing cycle commences with an increase in pressure via oil pumps until the maximum pressure is achieved. Following a brief holding period at the maximum pressure, a programmed decompression process begins. This series of fixed steps results in the removal of all pressure. The end product of isopressing is a crucible marked by the highest possible density, minimal porosity, and a uniform material composition extending from the bottom to the rim. This technique ensures that every crucible boasts consistent and predictable performance, essential in industries where quality and reliability are non-negotiable. Coking. The coking step represents the transformation of crucible binders from their initial, relatively impure organic state into highly pure elemental carbon. This metamorphosis is pivotal in ensuring the crucible's suitability for use in various industries. In preparation for coking, large empty crucibles, remnants from prior batches, are assembled on small flatbed rail cars. These rail cars are strategically positioned for loading. Green silicon carbide crucibles, having completed the drying process, are then arranged on the loading deck in order of size, from largest to smallest. A lifting device is employed to transfer each green crucible into a holding crucible on the rail car. This process continues until the smallest crucible is nested within the center, akin to a Russian matryoshka doll. The gaps between and around the green silicon carbide crucibles are filled with Boyd grains. A system of rails and shuttle cars transports the crucibles to the entrance port of the gas-fired tunnel kiln, a behemoth spanning more than 157 feet and operating around the clock. The green crucibles, protected by their buoyed covering, embark on a journey through the kiln, reaching sustained temperatures that often exceed 1000 degrees Celsius, 1800 degrees Fahrenheit. The outcome of this process is the transformation of the crucible's binders from their organic, impure state to highly pure elemental carbon. Coking serves as a pivotal transformation that primes the crucibles for the rigors of industrial use. This step ensures that the crucibles can withstand extreme temperatures and conditions without compromise. Impregnation. Impregnation is a thermal and chemical process designed to bolster the internal structure of crucible materials. This enhancement extends the crucible's service life, making it a reliable asset in demanding industrial applications. The impregnation process commences with the loading of crucibles into a specialized steel tank, serving as both a vacuum chamber and a pressure vessel. The chamber is subsequently filled with an impregnation solution and heated. Once the chamber reaches the desired temperature, it is pressurized. During this process, the impregnation solution infiltrates and fills the crucible's pores, ultimately solidifying to become a permanent component of the crucible structure. The result of the impregnation process is crucibles with reinforced internal structures, ensuring that they can withstand the most challenging industrial environments. Spout installation. Crucible designs frequently incorporate spouts to facilitate controlled pouring. The integration of spouts varies based on the crucible's type and application. Some crucible products feature spouts molded or formed as an integral part of the crucible during rib forming, roller forming, or isopressing. In other instances, the pouring spout is cast separately from the crucible and attached during the crucible's manufacturing or installation in the customer's furnace. Spout installation is a precision process. It commences with the craftsman using a steel file to shape the preformed spout's contact surfaces to match the crucible's curvature. The spout's position on the crucible is carefully marked, and its contact surface dimensions are transferred to the crucible surface using an etching tool. The craftsman follows these markings to cut a roughly shaped notch in the crucible's rim. The meticulous work of finally shaping both the crucible and the notch begins. It demands the accuracy of a skilled craftsman's eye and well-practiced hands. The objective is to ensure that the spout fits snugly, provides the correct pouring pitch, and remains perfectly level with the crucible's top. These intricacies are essential to guarantee controlled and precise pouring in industrial processes where accuracy is paramount. Glazing. The crucible's materials, including carbon binders and graphite, are susceptible to burning when exposed to heat and oxygen. To safeguard the crucibles from oxidation and to enhance their performance, durable glass-like glazes are applied. These glazes are engineered to deliver specific performance characteristics, such as resistance to chemical attack, thermal shock, and physical damage. Each crucible undergoes a glazing process, reinforcing it against the elements it will encounter in its intended applications. The selection and application of glazes are conducted with precision, and the crucibles are ready for the next stage in their journey. Inspection, painting, and shipping. After being subjected to a series of intricate processes, each crucible undergoes meticulous inspection. Experienced quality control professionals evaluate each crucible, ensuring that only those meeting stringent standards progress to the next stages.